So this is a live mussel in a jar filled with rocks, and you can see its foot moving around. It takes energy to move, and animals prefer to use oxygen in order to make their energy. And back in 2011, I had a couple of students that were keenly interested in measuring how much oxygen our freshwater mussels use. So they embarked upon a respiration study that summer. I'll tell you a little bit about that here in the next few slides. And this is a view from the top of a mussel. And here, water goes in through this kind of fuzzy little area here. That's called the in-current aperture or in-current siphon. And anyway, the water circulates around inside the mussel, passes over its gills, and then it exits through this other hole that's called the excurrent aperture or excurrent siphon. And while the water's in the mussel, of course, some of the oxygen that's in it gets removed and used by the animal. During the summer of 2011 and 2012, we set up a respirometer, a little homemade device that basically was a round plastic box within a larger plastic box full of water. And there's a little bar in the bottom here that buzzed around to stir it up to keep the water nice and mixed within the inner chamber. And then there's the mussel, right? So it's busy taking oxygen out of the water. And then every minute or so, I think it was every 60 seconds, we used this piece of stainless steel here. This is an electrode that measures oxygen concentration, and that's hooked up to a meter over here that gave us every minute we'd record the oxygen concentration in the water. And by doing that for a period of time, half hour or an hour, we'd get a nice slope, and we could measure how much oxygen that individual mussel was using per minute or hour or whatever. So that was our project. Essentially, we would pick up a mussel from the mussel bed, put it in a cooler, bring it down to the field station on the shore of Crooked Lake, and then do our stuff in the lab, and then we'd go get another one. So in order to make sure that we weren't accidentally measuring the respiration rate of the same mussel again and again, we tagged each one before we would put it back out in the lake. So in addition to the usual weighing and measuring, we would clean off an area up here next to the hinge, just posterior to the umbo, and we glued a shellfish tag to the individual, let it dry for about a minute, and then he was ready to go back to the lake. And notice I said we did one. When we started out, those first couple of years, we weren't intending for this to go on and on for a long time. We just stuck one tag on each mussel. And when we were done, we'd put our mussel back in a cooler, get in the boat and run it down to the mussel bed, put it back in the same place as we found it, and grab another one. And after thinking about this for a couple of years, we decided to embark on a more long-term tag and release study. And the first one we did was in October of 2015, and at that time we started to tag each mussel that we tagged with two tags, one on the left and one on the right. Basically, in case one of them fell off, we would still have the other number. And although our methods have stayed pretty much the same since 2017 with regard to tagging, our initial purpose for doing this was to attempt to gather enough data after repeated captures that we would be able to calculate growth rates, changes in weight and shell size and all that. But another thing that a person can do with tag and release data is to get an estimate of population size, that is how many individuals are living in an area. And that really is the point of today's video. Actually, this is going to be at least a two-parter because there's quite a lot of math going on. And I don't want to make this too terribly long. So we're going to use some of our tag and release data, our recaptures of tagged individuals to estimate population size. The first method that we're going to use is really simple. It's been around for a long time, and it basically says that the population size divided by the number of previously marked individuals is equal to the total number recaptured divided by those that were recaptured with marks. And of course, mathematicians like to reduce things to symbols. So we're going to use a convention here. We're going to define each of these sort of phrases, and we're going to boil them down to individual symbols. So population size is big N, uppercase N, divided by uppercase M, which is the number that were previously marked. And then total recaptures is going to be little n divided by little m, which is the number that are recaptured that have marks on them. And when you do a little, third grade algebra, if you take and multiply both sides of the equation by m, you wind up with the m winding up over here on the top on the right side. So what we have left is the population size, big N, equal to all the other letters arranged like that, okay? Now you'll notice on this bottom equation, I've added a little mark, we call that a hat. So the big N has a hat on it. And what that means is we're never going to actually know for sure in this Vale of Tears what the population size is precisely. Not unless we go out and we count every single individual, which is usually impossible or really, really difficult. So that little hat means an estimate. So what we're actually going to be determining here is the estimated population size, or capital N with a hat on it. I attended Omaha-Benson High School, and it has one of the coolest mascots I'm aware of. Omaha-Benson is the home of the Mighty Bunnies, and this was the logo that we used when I was in school back in the 1970s. It's also kind of interesting, I think, that my name is Warren, and if you look up Warren in the dictionary with a little case W, it actually means an enclosure for breeding rabbits. So back in the Middle Ages, medieval times, folks over in England used to create these elaborate underground burrow systems that they would install bunnies into and sort of farm the bunnies. Anyway, the Omaha-Benson is going to be our example for understanding how this works in practice. So let's say we wanted to know how many bunnies live or are in this building. Right? We don't know. And we're gonna devise a little experiment by which we can get an estimate of what the population is inside that building by trapping and tagging and releasing and then recapturing some of those bunnies subsequently. And I'm using an example that came right out of Smith and just sort of adding my own spin on it, mostly for entertainment value, mostly for myself. Okay, so let's say on a Tuesday, we captured, tagged, somehow or another got ourselves a hold of a random bunch of bunnies from Benson High School. And we put marks on them, ear tags, something. We put little something on each one, so we'd be able to know later on if we see it again, we'll know, on Tuesday we had that one in hand. So on Tuesday we captured, tagged, and released 39 bunnies. And then we came back a couple days later on Thursday and we recaptured, we randomly selected 34 bunnies on that day. And if you look at them really close, you'll see, well, that one there has an ear tag, and that one there has an ear tag, and but that one there doesn't. So this one is new to us. We did not capture that one before. Okay, here's another one and another one that don't have ear tags. And just for the sake of organization, let's put all of the ones that have ear tags together, count them up, and we find that out of those 34 that we recaptured on Thursday, 15 of them had been previously marked. And 19 did not have marks, so no ear tags. So putting that into a form that's useful for our little formula from Smith, we had 39 bunnies that were previously marked on the Tuesday, and then little m recaptured on Thursday. 15 of those had marks. And then the total that we recaptured on Thursday, little n, was 34. Okay, and our goal here is to get an estimate of the population size. So taking our formula from Smith and substituting our values in for those letters on the right side, we get that. And when we do the math, 34 times 39 divided by 15 gives us 88.4 bunnies. And 0.4 bunnies is really kind of a messy thing. So let's not go there. Let's put our value in whole numbers. So we could say that our estimated population size of bunnies is 88. Now, if we left it at that, it would give sort of a false impression of precision. There's a lot of variation going on in all of this. There's random selection going on. If you did this on a different day, you might get different, slightly different numbers that were had been previously tagged that were recaptured. You might have a different total number that were recaptured, and so on. So if you did this a whole bunch of times, you would get several different values for the population estimate. And Smith also provides a measure of variation to go along with this population estimate, and that's a standard error estimate. So we're going to calculate next using the same values for capital M, and little n. We're going to find the standard error for our population size. And the equation for that looks a little bit more intimidating than our previous one for population size, but it's really not too bad, which we'll just walk you through it here, and you'll see that this isn't really tough to do. So again, when we substitute our values over here for big M, m, and little n, we put those in there. We have everything we need now to calculate the standard error. And in this case, when you plug those into your calculator, you wind up with a value of a standard error of 17.06, which rounds to 17 bunnies. And a nice concise way to write that is 88 plus or minus 17 bunnies is the estimated population size plus or minus a standard error. Now, knowing the standard error gives us the ability to calculate something called the confidence interval. And to do that for this method, we can basically take the standard error, multiply it times 2, and then add and subtract that from our population estimate. So let's do that. So in our little example, the standard error was 17. Multiply 17 times 2, that gives you 34. And if you take 34 and subtract that from 88, you get 54. 88 plus 34, so 2 standard errors, is 122. So we can now make this little statement that there's a 95% probability that the number of bunnies is between 54 and 122. Well, that lays the basis for what we're going to be doing in our next video. So what we just did would be fine if all we did was go out and tag and release a bunch of mussels on a Tuesday and pick them up a week later or a few days later. But there's a lot of assumptions that go along with using that method that we just worked through. And those assumptions include things like there's no death, there's no birth, there's no immigration or emigration. That is, there's no mussels leaving the area or coming back to the area. There's no tag loss, blah, blah, blah. And what we know is we don't live in a perfect world. We live in this world, and so do our mussels. And we've been retagging, or we've been tagging mussels for a number of years. So, like I said, starting off in 2015, and we've been doing them pretty regularly ever since. Sometimes we tag new mussels that we've never tagged before. Sometimes there's new ones come in. So we need a method that's more robust than the one that we just outlined. We need one that's going to work for the real world, and that will be the topic of the next video. So you can look forward to that in about a week. See you then. Bye.